Thank you. So this mini course, like Alvaro said, it's concerned with abelian extensions, and one of my goals is to sketch out an argument for the Kronecker-Weber theorem, which says that if you have an abelian extension of the rational numbers, then it's contained in a cyclotomic field. But I actually don't want to assume that everyone has seen and is super comfortable with Galois theory. So for most of today, we're going to have the crashiest of crash courses in Galois theory. I'm probably not even going to state the fundamental theorem of Galois theory today, but I do want to define some of the terms and some of the important objects that you see in a statement of Galois theory. And just as a caveat, I'm going to focus on finite Galois theory. There is an infinite Galois theory, but I'm not going to touch on it very much, if at all. Okay, so notation. I'm going to use L over K to denote a field extension. This means that L is a field and K is a subfield of L, and even if you haven't spent much time thinking about field theory, you have seen field extensions before. So examples include the complex numbers over the real numbers over the rational numbers. Alvaro was just talking about finite fields. So if I have a finite field with p to the f elements, it is an extension of the finite field with p elements. And if you've ever seen all of the rational functions, so these are quotients of polynomials where the restriction is just that the denominator is not identically the zero polynomial. This is also a field over the rational numbers. And if we have an extension of fields, then L is a K vector space, which means that we can talk about the dimension, although the dimension need not be finite. Okay. And so our first definition is the degree of the extension, which is just the dimension of L as a K vector space. We have special notation. Which is this brackets L colon K. And like I said, it's the dimension of L as a K vector space. And I won't write it, but I'll just say it. The dimension of C over R is 2. The dimension of R over Q is infinite. The dimension of Fp to the F over Fp is F. And this is yet another infinite extension. Okay. One of the things that we get when we are dealing with finite extensions is that they are already what we call algebraic, which means that when I state the fundamental theorem of Galois theory and when I state the definition of a Galois extension, I'm not going to need to refer to the fact that these are algebraic extensions, but because I might use this language, I'm going to go ahead and define what an algebraic extension is, or I'm going to define what an algebraic element is. All right, so what is an algebraic element? If L over K is an extension, an element of L is algebraic over K. This is a relative notion. If it's the root of some polynomial with coefficients in K. And if such a polynomial exists, then there is a polynomial that has the smallest possible degree. And if you put an extra condition requiring that that you're dealing with polynomials that are monic, then the smallest degree polynomial that is also monic is unique, and we call that the minimal polynomial of alpha over k. And I will often denote this as m sub alpha k, again to emphasize the fact that this is a relative notion. So when I write m sub alpha k of x, I'm referring to the minimal polynomial of alpha over k. Okay. Not everything need be algebraic. So for example, if I choose a random real number, there's like a 0% chance that it's actually algebraic over q under some notion of percentage. Things like pi and e are not algebraic over q. But things like square root of 2, square root of 3, cubed root of 2, those are algebraic over q. Okay. An important and useful fact. We are only going to be dealing with perfect fields. There are things that we get to assume because we're dealing with perfect fields and we're dealing with finite extensions of perfect fields that's going to make some of the definitions that I'm giving you a little bit easier to get your hands on. But again, I give the caveat that these are not the general definitions of all of these terms. Okay? So one thing that we get by virtue of the fact that we're dealing with perfect fields is if L over K is a finite extension, then there is some element of L that I can use to work with a very nice basis for L over K. So I can express L as K adjoin theta, and by this, I really mean the smallest field that contains both K and theta, but one of the things that we get, because again we're dealing with finite extensions of perfect fields, is that these fields, you can express them in this way. So you can take K linear combinations of powers of theta, and we're going to liberally use this. In this setup, the degree of the extension, i.e. the dimension of L over K, is going to be equal to the degree of the minimal polynomial of theta. And I'm not going to prove or justify any of this, but I am going to freely use this fact. And another thing we get by virtue of dealing with perfect fields is that we are guaranteed that this polynomial has as many roots as possible. The maximum number of roots we can hope for is degree of m sub theta k roots. And so the degree of the polynomial is exactly how many distinct roots we have over some algebraic closure of k. Okay. Some examples. I'm picking away at the easy examples, partly just to help ground everyone and also to convince you that you have seen some of these things. They're not super scary, at least not at first. All right, so example, the complex numbers, it's R adjoint I. right? If I ask you to write down a random complex number, you might write it as a real number plus I times another real number, right? So you're already familiar probably with something like this. If I adjoin to Q a cubed root of 2, and again by this I mean the smallest subfield, let's say, of the complex numbers that contains a cubed root of 2. And typically when I write this, I mean a real cubed root of 2. But we can express this as this business here. Okay, so not that scary. Again, this is a degree 2 extension of the real numbers. And this, like I've given you a basis. I'm basically telling you that it's a degree 3 extension of Q. And it's not an accident, again, that the degree here, that I'm taking a cubed root of a thing, so the minimal polynomial, as you might guess, it's x cubed minus 2. It's degree 3. I have a degree 3 extension. These things all coincide. Okay. Galois theory is about the connection between certain kinds of field extensions and certain groups. And so let's start talking about the groups in question. Right? So when we talk about Galois theory, we're talking about a group that captures the ways in which you can move things around the field L, but you don't want just any old movement, right? We're dealing with fields, which means that we have some structure. We have some algebraic structure involved. We've got some addition, we've got some multiplication, and we're interested in the functions that preserve that structure. So whenever we use the word automorphism, you should always have in mind that you're talking about some sort of function that preserves a particular structure. And again, here we're dealing with fields, and so we're interested in functions that preserve the field structure. Excuse me. So if L is a field, an automorphism of L is a bijection sigma satisfying these two properties. If I give you any two elements of L, then sigma respects the addition, meaning I can do addition inside of the argument, and I'll get the same thing as if I first apply sigma and then do addition outside. And also, it preserves multiplication. And I'm hoping everyone has seen group theory. This is essentially homomorphism language, right? Here I'm saying I have a homomorphism of abelian groups under addition, and here I'm saying I have a homomorphism of the multiplicative group. Yeah. If you're wondering if you've seen field automorphisms before, you might have seen something about sigma of 1 being 1. That is forced by this condition here. So I'm not giving you a definition that you haven't seen before. If you've seen the definition of a ring automorphism, there are things that I'm sort of hiding in the fact that this is a bijection. If you haven't worked with field automorphisms before, then an important fact is that the set of all automorphisms forms a group. You should prove that for yourself if you haven't seen it before. And in particular, if L over K is a finite extension, or actually any extension, then the set of automorphisms that fix K element-wise forms a subgroup of the full automorphism group of L. So, exercise if you haven't done this before. So the set of all automorphisms is a group under function composition. And if L over K is an extension, then the set of automorphisms of L that fix K, which we often denote by aught L over K, that fixes K element-wise. So I'm not just saying that it sends K to itself. I'm saying that every single element of K is fixed by the automorphism. This is a subgroup. Okay. Another important exercise, if you have not done this before, but even if you have, maybe do it again to refresh yourself about how this works. I'm about to use this fact, but I am leaving it as an exercise. Suppose L over K is an extension and alpha is algebraic. Oops, over K. Suppose also that sigma is in the set of automorphisms that fix K element-wise. Then one, if f of alpha is 0, so too is alpha of sigma alpha. In other words, if I have an automorphism, I have to send roots to roots. And once you've established this fact, if you have a finite extension, and let's just go ahead and give ourselves what we call a primitive element. Then this gives us a bound on the number of automorphisms of L that can fix K. All right. This. Welcome. Oh no, you're asking me to do things in physical space. Better? I did it. All right. Quick example. I get to do the easy examples. I'm making y'all do the slightly harder examples. Suppose I have some automorphism of Q adjoins square root of 2 over Q. Again, this is just the smallest subfield of the complex numbers in which I have a square root of 2. As you might guess, a minimal polynomial for square root of 2, the minimal polynomial is just x squared minus 2. Okay. Then, assuming the result of the exercise, sigma of square root of 2 has to be equal to plus or minus square root of 2. Here we're just using the fact that if I take this thing and I square it, I'm asserting that it has to be equal to 0. And my claim is this completely determines what this automorphism group can be. Right, so what this is saying is either I did nothing to square root of 2, and my claim is in that case I have to be dealing with the identity function, or I flip the sign on square root of 2, in which case I have an automorphism that if I do it twice, I'm going to get back the identity. Okay, so that's a claim, but you should also prove that for yourself. One of the exercises I have for you is to prove that if I replace square root of 2 with, say, cubed root of 2, I actually don't have any automorphisms. So part of what I'm claiming over there is that I have 2 automorphisms, which is the maximum number of automorphisms I can have because this is a degree 2 extension, right? So again, this degree gives us a bound on the size of the automorphism group of, in this case, Q adjoin root 2 over Q. But it's an exercise for you to prove that this field extension, where I give myself a cubed root of 2 instead of a square root of 2, that it's the trivial group. Right, so my claim is I have no non-trivial automorphisms of this field. If you haven't seen this before, then try it for yourself, see if you can sort of wrestle your way through to it. But if you really, really, really get stuck, you can come see me, and I will give you the key hint. There is a special number that is missing here. If you really think about, like, what are the cubed roots of 2 have to do? Like, what do they have to look like? You can sort of fight your way to an argument that I don't have all of the things that I need in order to be able to move roots around, right? I only get one of these roots when I really need to have at least 3 of them. Okay, so what is the difference between this field and this field? What am I missing here that I have here? Well, I already kind of hinted at it. I have all of the roots that I expect to have here, and I am missing some of the roots that I would like to have here. And that is the difference between Galois and not Galois. There are numerous equivalent ways of stating that an extension is Galois. I'm going to give you one of the standard definitions, and then I'm going to give you a couple of equivalent conditions, and we'll just move between these 3 equivalent ways of showing that something is Galois, depending on which is easiest for whatever application we have, right? So again, I'm only stating this for finite extensions. A finite extension is Galois if 1, it's what we call a normal extension. This just means that if I have a polynomial, f of x, that is irreducible and it attains a root in L, then it attains all of its roots. Right? So if I pick up a root for a polynomial, I'm picking up all of the roots for that polynomial. I feel like I'll just go with it. Okay, that's the normal condition. There's also a separability condition that we are mostly not going to worry about because we're dealing with fields either of characteristic 0 or because we're going to be referencing them for the Kronecker-Weber theorem, we might be dealing with finite fields. But in all of those cases, we have a condition on separability that we're not going to have to worry ourselves about. If you're really, really interested and want to see an example of an extension that's not separable, so it has all of the roots for an irreducible polynomial, but it's somehow not separable, so it's not Galois, you can come see me after lecture. This is a characteristic p greater than 0 phenomenon. Okay, so you don't encounter it with the fields that you might be most comfortable with, like Q or R or C. It's a joke. C doesn't have any non-trivial extensions. Okay. So second condition. This is separability. So separability is about having as many roots as the degree of the minimal polynomial tells you you should have, right? So if I have a degree n polynomial, I expect n distinct roots. And implicitly, I'm saying something about algebraic closures, but I'm not going to belabor the point. If you want to just think of, for right now, working in some subfield of the complex numbers, then all we're requiring is that it has distinct complex roots, so n distinct complex roots, if the degree of the polynomial is n. Okay. Like I said, luckily for us, we're working with perfect fields. One of the things that we get because we're working with perfect fields is that every irreducible polynomial is separable, which means that when we're looking for Galois extensions, the condition that we most need to concern ourselves with is this normal condition. So really, for the cases that we're interested in, what we want to know is, when I attain a root of some polynomial, am I getting all of the roots of that polynomial? That will be the defining characteristic of Galois for us. Again, separability is a concern in general, but we're in the nice cases where we don't have to worry about it. This definition, it's important. It can feel a little bit hard to work with, especially in practice. Like if I give you a random extension, let's say I give you some finite extension of Q, I give you some random number field, and I ask you, is this a Galois extension? I mean, yeah, I already told you this is the condition that we most concern ourselves with. This is a thing that you can check, but like, how do you actually know that that an extension is Galois? Is there some other condition besides just finding an irreducible polynomial and guaranteeing, or looking for all of the irreducible polynomials that attain a root and making sure that all of them have all of their roots in whatever your field extension is? Happily, we have, like I said, some equivalent ways of saying that an extension is Galois. And so I'm going to give you this theorem, and we're going to use it. This really is, I'm using the fact that L over K is finite here. All right, if L over K is a finite extension, then the following are equivalent. 1, L is a Galois extension over K. 2, the size of the automorphism group is as large as it can be. And 3, L is the splitting field of some polynomial with distinct roots. And here I'm not making any claims about a polynomial being irreducible. I'm not making any claims about the degree of the polynomial. I'm just saying if you can exhibit for me some polynomial that you know has distinct roots and you can recognize L as a field in which all of the roots of that polynomial live, then L is Galois. Okay? When any of these equivalent conditions is satisfied, we use Gal L over K for the automorphism group. So if I write automorphism of L over K, I'm not making any claims about whether or not the extension is Galois. But when I write Gal of L over K, I'm specifically indicating that it is a Galois extension, and I'm going to assume all of the things that come along with being Galois. Okay, so I've defined all of the things that I need in order to finally tell you what an Abelian extension is. All of this was prep work for the title of the lecture that I erased earlier. So, a finite extension, L over K, is Abelian if its Galois group is Abelian. But remember, I'm only writing gal of L over K if I know that the extension is Galois. So abelian extension doesn't just mean that the automorphism group is abelian. It means that it is a Galois extension whose automorphism group is abelian. So in this case, I would not claim that this is an abelian extension because it's not even Galois, right? I do have an abelian automorphism group because it is the very exciting trivial group. It's not a whole lot you can do, but I don't want to think of this as an abelian extension. Great. Some examples of abelian extensions. You have seen them even if no one said to you, these are abelian extensions. You have seen things like this before. Already today I've given you some. We've already seen C over R. The complex numbers are famously algebraically closed. They're the algebraic closure of R. This is a Galois extension. If you're away from characteristic 2, every quadratic extension is going to be Galois. You don't have very many choices for what your Galois group can be. It's a degree 2 extension, which means that it's a group of order 2. Up to isomorphism, there's only one, and it's abelian, right? So it's abelian with the Galois group isomorphic to C2. That's my notation for a cyclic group of order, in this case 2. And the non-trivial automorphism is the one that you would guess if I asked you, give me a non-trivial way of moving the complex numbers around. You might say, well, just do complex conjugation. That is the non-trivial automorphism of C over R. And in this case, if I'm making a quadratic extension, it's because I'm giving myself a square root that I didn't have before. The square root that I'm giving myself that I didn't have before was just a square root of -1, right? Here, if I give you a square root of some square-free integer d, this is also abelian. And its Galois group is, again, I don't have very many choices for what it can be. And let me say, since I'm talking about the fact that these are Galois, I should be a little bit honest and say, what is it a splitting field of? This is a splitting field of, amongst other things, bless you, x squared plus 1. This is a splitting field of x squared minus d. If I give you a prime p, and I give you any finite extension of fp, that is an abelian extension. In fact, it's not just abelian, it's cyclic, so it's not just an arbitrary abelian group. It is, in particular, a cyclic abelian group, and it's generated, the cyclic group is generated by something we call the Frobenius. So it's the Frobenius map. So extension of finite fields, cyclic, and therefore abelian, and it's isomorphic to the cyclic group of order f. And this is a splitting field of x to the p to the f minus x. And lastly, the extensions that we're going to be most interested with, at least for the next couple of lectures, the cyclotomic extensions. And I'm going to cheat you because I'm going to tell you that they're abelian. I'm giving you an exercise to essentially show that they're abelian, but I'm not going to do the work. You're going to do the work. I'm going to use, this is my version of a zeta, don't judge. This is zeta sub n. I'm going to use that to denote a primitive nth root of unity. And don't worry if you don't know quite what that means. I'm going to go over that a little bit. This is a splitting field, or the splitting field, of the polynomial x to the n minus 1. I am asserting that this is an abelian extension. I'm leaving it to you as an exercise, but in order to show that this actually is an abelian extension, for one thing, I'm giving you the polynomial that I'm claiming it splits. You should prove that all of the roots of this polynomial live inside of this field. Okay? You should also make some argument for why the Galois group is abelian. And I'm going to try to set you up with a little bit of information about a choice you can make for zeta n that might help smooth things for you, so help you move things along. Okay. First, what do I mean when I say zeta n is a primitive nth root of unity? Zeta is a primitive nth root of unity if, well, first, I should be able to raise zeta to an nth power and get 1. That just means that it's a root of unity, an nth root of unity. When I say it's primitive, what I'm saying is n is the smallest positive integer for which this is true. If you're more comfortable with group theory language, one of the things that I'm saying is that if I take the group of all nth roots of unity, one claim that I'm making is that it's a cyclic group. And when I refer to a primitive nth root of unity, I'm talking about a generator for that group. But notice that I'm saying a generator and not the generator because, in general, you have choices. Here I'm going to deal with roots of unity inside of C. You can talk about roots of unity over other fields. Over fields of characteristic P, you have to be a little bit careful if P divides N. You shouldn't expect nth roots of unity in that case. But in C, I said in general, you have some choices, not for zeta 1 and zeta 2. Zeta 1 has to be 1. It just has to be. You don't have any other thing for which zeta to the 1 is equal to 1. It's just 1. Similarly, you don't have any choices for zeta 2. It just has to be negative 1. Okay. You do have a choice for zeta 3. Here's one. And for zeta 4, you also have a choice. I'm choosing I. I could just as easily have chosen negative I, and it would have still been fine. And how was I choosing those specific examples? Or how was I choosing those examples? I chose them by sort of looking at the unit circle in the complex plane, identifying the smallest angle that will sort of give me what I want. I'm waving my hands here, but if you want a geometric picture, again, you can see me afterwards, and I'll sort of show you the picture that I have in my head. But with the geometric picture that I have in my head, I'm making a particular choice for zeta n. And it's this complex number. And because it's helpful, especially if you have not seen something that looks like this, I'm just going to tell you Euler's formula and encourage you to use it when it's helpful. Euler's formula says if I have any real number theta, bless you, then e to the I theta is equal to cosine of theta plus I sine of theta. This choice is really helpful for doing the exercises that I'm asking you all to do. For one thing, you can use this to show, so you can use this formula to make an argument for why this is a primitive intrusive unity. The fact that it's an intrusive unity falls out relatively easy from this formula. The fact that n is the smallest integer for which this works, use what you know about cosine and sine, right? If I want something like this to be equal to 1, I know what theta has to be, and I know what I know what cosine of theta has to be, and I know what sine of theta has to be. And the restriction that I get a 1 out of this is saying I want cosine to be 1, I want sine to be 0. You know exactly the kinds of angles that make that true. All right. Great. So here's the exercise, or here's an outline for the exercise that I would like you to do. We're going to choose the zeta n that I told you, so e to the 2 pi I over n, complex number. I want you to show that zeta n to the nth power is 1. If I take any other power of zeta, it is also an intrusive unity. For any pair of integers between 0 and n, so greater than or equal to 0, k strictly less than j, strictly less than n. These are not the same number. From this, you should conclude that there are exactly n distinct solutions to x to the n minus 1 that I can express in terms of zeta n. All right, so this is an argument for the fact that the extension Q adjoins zeta n, which we call the nth cyclotomic field, is a Galois extension, but that's only half the battle, right? I'm telling you it's a splitting field. I'm giving you an argument for why it is the splitting field of this separable polynomial. One of the things that you're proving is that this polynomial has n distinct roots, right? You didn't do something weird like try to say x squared minus 2x plus 1 has 2 distinct roots. It doesn't. It's not a separable polynomial, but this thing does. That's essentially what this argument is about. But like I said, that's only half the battle, right? I'm claiming it's an Abelian extension. Okay, this is when I insult you slightly and we pretend you're in kindergarten. All right, class, this is only half the battle. What is the other thing that I have to show? Y'all are on camera being caught being very quiet. Don't be those people. The Galois group is Abelian, right? This is the claim that it's Galois. The Abelian part is still left to prove. And we've already done at least a little bit of work to determine what the automorphisms of the nth cyclotomic field have to look like. What are the things that they have to do one of our arguments earlier, or one of the things that I'm asking you to show in the exercises, is that automorphisms are basically determined by where you send roots of a minimal polynomial. So if I give you something like this, one of the results of the exercise that I'm asking you to do earlier is to show that the nth roots of unity have to go to the nth roots of unity, but then that means that an automorphism has to be sending zeta sub n to some other power of zeta sub n, but not every power will do. Okay, you don't want to do something ridiculous like send I to 1. It's a bad idea. For those of you who are taking notes, look back at your notes of automorphism. What am I violating if I try to do something like send e to the 2 pi I over n to 1? So you have to fix the base field. There's another problem. They have to preserve the identity. Question/challenge. If I sent this to 1, have I actually violated anything about where 1 has to go? 1 will still go to 1. There's something else that's wrong. It won't be a bijection. I just said 1 has to go to 1, but I'm also sending this to 1. And remember, our definition of automorphism is it's a bijection, which means that it needs to be injective. Cannot send two different things to the same number. Okay? So we know, because you of the future will have proved this, that if I have an automorphism of the nth cyclotomic field, that I have to be sending this to some other power of zeta n, because one of the things that you're arguing is that these are all of the roots. All of the roots can be expressed as zeta n to some power. But we just gave ourselves a warning. Not every choice of k will do. If I make a choice for zeta 4 being I don't want an automorphism sigma to send I to 1 or even negative 1. Neither of those is going to preserve injectivity. So it's negative 1, but I'm going to write it as I squared because I said it's some power. Negative 1 is I squared. That's kind of how you define it. Okay. But if it's going to be an automorphism, it cannot do this. It can, however, send I to negative I. You recognize that as complex conjugation, but in terms of powers, which power am I sending I to? You're sending it to the third power. And so one of the things we should wrestle with in order to prove that the Galois group that we're dealing with is abelian is to first, again, establish the fact that zeta has to send an nth root of unity to some other power. But then there are only certain choices of a power that can work. Don't overthink it. I'm saying that I cannot send I to the 0th power of I or the 2nd power of I. I can send it to the 1st power of I. That's just the identity map. I can also send it to the 3rd power of I. Y'all indulge me a little bit. This is a 4th root of unity. I said 0 and 2, don't do it. But 1 and 3 are fine. What's the difference if I'm thinking about things, I don't know, say modulo 4. Say it again? They're co-prime to 4, right? So my claim / your exercise is to show that I can identify automorphisms of the nth cyclotomic field with things that are relatively prime to n. So if sigma is an automorphism of the nth cyclotomic field over Q. There is some A, and I'm going to confess to like stealing Keith's notation for this. I'm going to refer to it as A sub sigma for a reason that you'll see in a second, such that, oops, you do need this condition. GCD of A and N is 1. So that for any power of zeta n, the automorphism just raises zeta to the 8th power. Okay. And my claim slash the other part of your exercise is that this gives us a group homomorphism. But not just any old group homomorphism. This gives us an injective group homomorphism from the Galois group of the nth cyclotomic field into, think fast. I'm hoping that most, if not all of you have seen, oh, I just gave it away. I was going to ask you, if I'm describing the things that are relatively prime to A, first convince yourself that I really only care about these powers modulo n, right? If I took I and I raised it to the 6th power, I might as well have just raised it to the 2nd power. It's no different, okay? But my claim is that this is giving us a homomorphism, an injective homomorphism from the Galois group of the nth cyclotomic field to the units of Z mod NZ, because that is what this condition is about, okay? But if this is an injection, then there's a very important theorem about homomorphisms of groups. Say it again. First, exactly. Exactly. The first isomorphism theorem for groups tells you that the image of this group and here is isomorphic to this group modulo the kernel of the group homomorphism, but I'm claiming it's injective, therefore the kernel is trivial, which means that I have a copy of this group inside of here. And huzzah, you, like future you, has proved that this is an abelian extension. Aren't you so proud of your future self? You did such a good job. Oh, my claim is that the homomorphism is sigma goes to A sub sigma mod n. No pressure to future you, but like they did a lot, so I don't know, when you catch up to your future self, make sure you haven't disappointed yourself. You did it. All right. Like I said at the beginning of this lecture, one of my main goals is to sketch out the proof or a proof of the Kronecker-Weber theorem. And if there's time after we give one proof, I will at least wave my hand at some of the other ways in which people can prove the Kronecker-Weber theorem. But we've done a little bit of work. I've given you two kinds of abelian extensions over Q, right? Quadratic extensions, I'm giving you cyclotomic extensions. The Kronecker-Weber theorem says that these kinds of extensions essentially account for all of your abelian extensions. So it's not saying that every extension is a cyclotomic extension. That's not really what Kronecker-Weber is about. But it is telling you that every abelian extension is contained in some cyclotomic extension. And Keith has some very nice notes on the history of the Kronecker-Weber theorem. Even though it is named the Kronecker-Weber theorem, the first proof that is recognized as being correct and complete was due to Hilbert. I think Keith can correct me if I'm wrong, if he's in here. Kronecker got the theorem started but he sort of sketched out an argument that was supposed to work for prime powers as long as you were dealing with an odd prime. It was not claiming to be complete for powers of 2. Weber gave an attempt at a complete proof, but long after he published it, there was an error that was found. Hilbert gave a separate proof, not knowing that there was a mistake in the original proof. I think he also believed that it was a correct proof. The error was found, like, I don't know, almost 100 years later. So Hilbert gave the first correct proof, and there have been subsequent proofs since then involving various techniques in algebraic number theory that, like I said, if we can get through a sketch of this, I will talk a little bit about the other methods for proving the Kronecker-Weber theorem later. Okay, so the Kronecker-Weber theorem says if L over Q is an abelian extension then L is contained in Q adjoins zeta n for some n. And for our last bit of time together today, what I'd like to do is give you a few examples. Some of them, they're just like, haha, of course. But some of them actually point towards something that's a bit nice. So one of them is going to involve Gauss sums. I played around with the idea of asking you to prove something about quadratic extensions in general. I might still do it, but I will also give you an example so that you can see kind of how things like the Legendre symbol can be used to show that a quadratic extension is contained in a cyclotomic field. Okay, here's our first haha example. I'm being obnoxious, right? It's contained in all of the zeta n's, fine. But it's also in Q adjoins zeta 1 because I'm being obnoxious. This is just Q again. And I'm gonna be even more obnoxious. I'm gonna say this is zeta 2 as well, all right? So Kronecker-Weber, in at least one case, check. Q adjoin I. Well, we've already identified I as a primitive fourth root of unity, so Q adjoin I is the fourth cyclotomic field. Okay. I exhibited a primitive third root of unity, and it was expressed in terms of rational numbers along with the square root of -3. And so convince yourself that I've basically given you the third cyclotomic field. This is also the sixth cyclotomic field. Okay. I'll open it up to you. I kind of want to do like the Jeopardy theme song in my head, but like if you haven't said hello to a neighbor, say hi to a neighbor, introduce yourself to someone. Like Alvaro said, one of the things that you get from being here is you get to meet math people. So I would like you to make a new math friend if you haven't already made one. Q adjoins square root of 2. See if you and a math buddy can figure out maybe which cyclotomic field that lives inside of. And see if you can make an argument for why. And not at all related, but I did give you Euler's formula. It does say things about sines and cosines. I don't know, maybe look for square root of 2. Oh, sure. Has anyone found a candidate in 8? If you look back at Euler's formula and you ask yourself, where might I expect a square root of 2 out of something like cosine of theta and I sine of theta? Maybe you're looking for something like pi over 4. Pi over 4, same as 2 pi over 8. So plug 8 into the formula that I gave you for zeta n using Euler's formula. You will get a square root of 2 out, but you also got some other stuff, right? You got an imaginary number out. But this is a totally real field. One of the things that you want to do is express this, so just this real number, in terms of that zeta 8. And so the question is, how do you get rid of the imaginary part? Those of you who have seen some complex analysis, I give you an A plus BI, and I want to get rid of the BI. Don't overthink it, but what might I do to get rid of it? Add the conjugate, right? If I add in something that involves a negative BI, I've killed off the imaginary part. So solution, Q adjoins zeta 2 is contained in the 8th cyclotomic field. Try something like, let's see, zeta 8 plus zeta 8 bar. I'm doing something slightly cheaty. This is convince yourself, exercise, prove for yourself that this is also a power of zeta 8. It's helpful maybe when you want to like explicitly do things with atomic elements to figure out which thing this is, which power this is. Try that. I think this is the one that works. If not, tell me I'm a lying liar who lies and tell me what works. Okay. So far so good? Yes.
That number there is the square root of 2, right? So could it be a power of zeta 8?
Great question. It is not exactly a power of zeta 8 because any power of zeta 8 is in particular a root of unity. And I can't raise square root of 2 to anything and hope to get a 1. But very good question. Yeah, so when we're dealing with linear combinations of powers of roots of unity, we can get out things other than just pure roots of unity. Right? So when we're making this claim about abelian extensions being contained in cyclotomic things, what we're saying is we can express anything in an abelian extension as a linear combination of some powers of a primitive nth root of unity, but the linear combination part is important. So I'm not claiming everything is a power of an nth root of unity, because I only have finitely many of those. I am claiming that I can use linear combinations, rational linear combinations, to express things in an abelian extension using powers of a cyclotomic thing. Yes?
Is there an algorithm to get F?
That is a great question. You're asking such a good question. For quadratic things, this is the exercise that I'm sort of like waffling back and forth about whether or not I want you to do this for quadratic things. For quadratics, yes, we know exactly which cyclotomic extension it lives in. This is related to something called the conductor. But I'm going to half answer your question by giving you an example of how you can find the cyclotomic, or how you can show that that Q adjoined root 5 is in the 5th cyclotomic field. And then I will tell you what the exercise was, but I will leave it to you if you want to, like, I don't know, do some quadratic things on hard mode and you feel like it's been a while since you played with the Legendre symbol. I'll tell you the exercise that lets you play with the Legendre symbol to show that certain quadratic extensions live inside of a particular cyclotomic extension. And then one of the things that we'll need to do for the proof of Kronecker-Weber is show that you can sort of reduce abelian extensions to the simplest possible abelian extensions. I will say more about what that means a bit tomorrow, but last 5 minutes. 5 minutes? Okay. So example, I claim that Q adjoined root 5 is in the 5th cyclotomic field, and do not trick yourself into thinking that Q adjoined square root of P is always in the Pth cyclotomic field. It's not quite that simple. But my claim is if I let G be equal to this strange looking combination, which is actually the sum from 1. This is an annoying way of writing 4, but it's because I have a generalization in mind of the Lozano symbol on 5 times, yeah, so 8 to 5 to the k. I claim that this is the root of x squared minus 5. And since we're low on time, I won't be able to go through the argument, but I'm happy to go over this during a break or during one of your problem sessions. But this obnoxious looking formulation, this is a way to show that Q adjoin square root of P is contained in a particular cyclotomic field. Again, it's, sorry, not Q adjoin square root of P. Q adjoin either plus or minus P, you do have to sort of choose the right one, is contained in the Pth cyclotomic field. And I think that is where we will stop for today, although I will happily answer any questions. Thank you.